So we have another great sequence of talks today on tap. So our first speaker is going to be Robert Nowak, who's going to be speaking about sequential analysis and high-dimensional multiple testing and sparse recovery.
Is this microphone to put on? Yes. Does it sound like this is doing something?
Hello? Hello?
I could just stand right here, too. All right. Can everybody hear me all right? No? No? Does it? So this thing? Hello? Whoa, gee. I'll put it right up here. Okay. Well, good morning. I'd like to thank the organizers, especially Becca, for all her hard work in putting together this wonderful workshop. Really enjoyed the talks so far, and looking forward to some more today. Let me tell you a little bit about the sort of beginnings of the work I'll discuss. When I was a kid, I pretty much fed myself on a steady diet of science fiction magazines and books and comics, and I was really fascinated with robots and artificial intelligence. And one of the key kind of ideas in all that was that you would have robots not only that you could teach and train, but they would become sort of interactive and begin to explore and learn on their own. And I think what I'll talk about today takes a little inspiration from those science fiction stories that I used to read. I also modeled my current lab after some of those stories. See me there with the brain on the desk and the robot in the background, and if you're ever in Madison, you're more than welcome to come and we can run some experiments on you. Okay, so here's the idea. I'm interested in what in machine learning is called active learning. In statistics or experimental design, it's called sequential experimental design. And this picture sort of shows the three components of sequential sensing, measurement, and experiment. We have a model space. These are the space of models or hypotheses that we're considering. We'd like to figure out which model is the right one for a problem at hand. We can run experiments or sensing actions or take certain measurements. That's the blue circle up above. And then down on the lower right, we have our data. These are the outputs of those experiments. And so the usual process of experimentation and sensing would go like this. We have a model space that informs some design of experiments. Those experiments produce data, and then we take that data and try to decide which model best matches the data we've observed. And what I want to think about is a situation where we don't just stop there. We take that data. The data certainly tells us that some models are more reasonable than others, but maybe we don't just try to pick the best at that point. We narrow our focus down to a subset of models that seem reasonable given the data we've seen so far, and then we repeat this process. And because we've now narrowed the focus of our search through the model space, that might suggest that new sensing or new experiments might be more efficient or more effective at teasing apart which of this smaller set of models is really the best. And so it's a kind of closed-loop feedback process, and that's what I want to talk about today. So let me give you a little bit of motivation for this. I talked a lot with various people in the biological sciences. This guy is Paul Ahlquist. He's at Madison. He studies virus replication. And one of the models that he works with is the fruit fly. And what they'll do is they take fruit fly cells and they'll introduce a virus deliberately and then look at how that virus replicates and grows within the cell. And what they're interested in doing is figuring out which genes and proteins are involved in the virus replication process. And to do this, they have a library of 13,000 different fruit fly cell strains. Each strain is the basic fruit fly cell, but with one gene pulled out or missing or repressed. And so what that allows them to do is they'll now introduce the virus into each of these different cell strains, and they'll look at how it replicates under those different conditions. And if they find a cell strain where the virus can't replicate, then they know that that particular protein and gene were very important in this virus replication process. And they can actually just kind of measure this by attaching a fluorescent marker to the virus, and then they put each cell strain in a little dish, put the virus in, and then look at how much it glows. And the more fluorescence, that means the more virus replication. So it's a fairly straightforward experimental process. And what they'll do at the end of the day is produce a kind of picture like this. The letters down below in each of those blocks are the names of different genes that are involved in different stages of the virus replication as the virus forms this little vesicle, and then it produces new virus strands within those. So that's what the ultimate product of their research is. And the first thing they need to deal with, though, is who are the players in this process, in this virus replication network, if you will. And so which genes are involved? And they have a nice Nature paper a few years ago where they found that there are roughly something on the order of 100 interesting genes out of the total number of 13,000 different genes in the fruit fly cell. And the way they did this is kind of an interesting thing. What they did is a sequential experimental design. They did a two-stage design where in the first stage they measured each of the different cell strains twice, and if in either of those experiments they saw some interesting variation in the fluorescence level relative to just the normal type of cell, then they would pass that strain on to a second stage because there's some indication that there might be something interesting going on in that particular strain. That brought them from 13,000 down to 1,000 different strains. And then for those remaining 1,000 strains, they actually repeat the experiment not twice, but now maybe 6 to 12 times. This allows them to boost the signal-to-noise ratio, and then they make a more sort of confident statistical determination about whether or not each one of those 1,000 remaining cell strains was interesting, and that brought them down to the set of 100 that they finally settled on. And so the reason they did this is because if they wanted to do, say, a dozen replications of all 13,000 experiments, it would have taken them several months, whereas they were able to do this type of two-stage design in a much shorter time span. And the hope is that they're getting the same information out. They're finding the same 100, but doing it in this more sequential process and focusing their resources for experimentation. Let me just show you a really quick picture to give you a kind of visual of what they were doing. You can imagine in the non-sequential design, they would just, say, measure each of the cell strains a few times, say 3. They would get a very noisy estimate, so that two spikes that you see in green there are supposed to be interesting genes. They make measurements, the experiments, they get some noisy data that's below there in blue, and what they'll have to do if you just make this one-shot experimental design is then you have to draw a line somewhere and say if you're above that line, you're interesting, and if you're below, you're not. So that's what that line represents, and you just say, well, everything below the line doesn't look interesting. And the problem is you might miss some signal there if you do that, and it can turn out that it might even be impossible to really distinguish between the signal, which is the interesting genes, and the noise in the process in experimental design. So that's non-sequential, but their sequential approach looks like this. So instead of just measuring everything once at a fairly reasonable noise level, they'll take one very noisy measurement of everything. So that's a very noisy measurement, more noisy than what you see on the left there. And instead of trying to now decide where are the interesting genes, they're just going to take a very crude threshold, like threshold at 0. Get rid of anything that's 0 because maybe that's probably uninteresting. And then they'll go back and refocus their experimental effort on the things that remain after that crude thresholding, and then try to make a statistically significant decision about where the interesting genes are. So that's their multi-stage design. And the hope is that what that second stage allows you to do, again, is boost the signal-to-noise ratio and make it easier to separate signals from noise. Okay, so good question is, does this kind of two-stage design or other multi-stage design actually help you? So let me just quickly tell you a couple of other applications where this could be useful. One is in spectrum sensing, where you want to sense where there are signals present in a very wide signal space. And there are a couple of ways you could do this. You could either measure each channel in that communication system for a fixed amount of time, or you could do something more adaptive and sequential, where you sort of vary the amount of time that you spend at different channels in order to make decisions as quickly as possible. And it turns out by sort of doing a more adaptive approach, you can potentially really speed up the whole sensing process. And I'll come back to that toward the end of the talk. Another problem is just this generic sparse recovery problem that we heard a lot about in the past day. You're looking at image reconstruction, compressed sensing, and so forth. This is the kind of picture that you'd usually see. You're trying to recover a sparse vector from some linear observations. And what we're interested in knowing is there some advantage to sequentially designing the rows of a sensing matrix, for example. And I'm not going to talk about this application, but Jarvis Haupt, who's also here, will have a poster on it, I think, Thursday. So I encourage you to check that out. So let me kind of explain now what is the kind of real challenge in all these problems. And that is that we have a huge number of possible models, each one representing a different sparsity pattern. So here is a demonstration of how this problem comes up. This is a paper that appeared at a conference and then was reported in Wired magazine. Some guys took a dead salmon and they put it in an fMRI scanner, and they found that there was significant activation in the brain of the dead salmon. And of course, that's just an artifact because there's always going to be some large noise deviations just due to the noises in the MR machine. And this was a warning that you really do need to be careful about this problem of trying to search through a huge model space with noisy data. Okay, so this is a cartoon that quickly illustrates the idea too. I like it, and I'll just go through it quickly. The idea is that jelly beans cause acne, and so they call on the scientists to investigate. The scientists look at jelly beans, and they find that at a p-value of 0.05, there's no significance for the claim that jelly beans are causing acne. And so that's settled, but then somebody said, oh, wait, hold on. I think it's only certain colors of jelly beans. So then the scientists look at all different colors of jelly beans, and most of the time they find nothing, but over here with green, actually they did find a link with green, okay? And then they make the cover of the news, and they're famous because we now know green jelly beans cause acne. And so the issue here is it's a fishing expedition, and if you look in enough corners, eventually just some random errors or noise are going to push you over that threshold. And if you don't correct for the fact that you're looking at things from so many different angles, you're going to get misleading results. Okay. So now let me kind of give you a mathematical formulation of this type of problem. So the single experimental model, we're measuring a sparse vector x. We see it plus noise, so the zi's are just Gaussian noises with unit variance. And we'll assume that x is sparse and let capital S denote the support set, the locations where there are non-zero elements in x. So here's what x looks like. It's mostly zeros, but it's got some non-zeros. And here's what the noisy observation would look like. And if we're trying to decide where are the interesting non-zero components in that noisy vector, a simple thing you might say is, well, let's just look for, if we're thinking of the non-zero components as being larger than 0, let's just look at the largest value. That's a natural candidate for at least one of those components. And we could take that as an estimate for the location of one of the non-zero components. And the problem is that even if we had no signal at all, just noise, if you give me n IID normal 0, 1 random variables, the largest noise is going to be on the order of square root of log n in magnitude. And so that means that the larger the number of dimensions n, the larger the largest noise in that process will be. And so you have to be careful about that. And it basically means that you're not going to be able to reliably detect signals unless the signal amplitude, which I'm going to call mu, exceeds that value of square root of 2 log n. If it doesn't, then it's basically, you can't be sure whether it's signal or noise. So instead of that single observation model, though, the sequential experimental design idea looks something like this. You're going to make a sequence of measurements. So now I'm laying I again, index my spatial dimension or location. J is going to be indexing my sequence of experiments. So I'm going to repeatedly measure different components of the signal. And each time I make a measurement, the noise level or precision of that measurement is going to be governed by this parameter gamma. So the z's are, again, just normal 0, 1 variables, but the gamma ij's are something that I'll modulate to control the precision of each measurement. So if I make gamma larger, I get a smaller noise. If I make gamma smaller, I'll have a larger noise. And the total precision budget we're going to constrain, and the way that we're going to do this sequentially is we're going to allow gammas to depend on past observations. So we're going to adapt those as we go. So here's that sequential measurement model. In order to make a kind of apples-to-apples comparison with non-sequential methods, we're going to constrain the total precision budget to be n, which is the same as the budget that we would be using if we just measured each of the n variables in this multidimensional signal one time. So for example, if I took k, the number of measurement steps, to be 1 and set all the precision parameters to be 1, then we get exactly back to this single experimental model that I talked about before. So how do you, what do these precision parameters mean? Well, basically, you could think of them as our knob that we can control the signal-to-noise ratio at each location and at each step of the process. And we can increase the signal-to-noise ratio by making more repeated samples at a particular location or measuring for a longer period at a particular location. We can make the SNR lower by making fewer measurements at a particular location. So it's a very natural sort of knob that you might be able to control in an actual experiment. And it's exactly what Paul Ahlquist and his group were doing in their experiments. OK, so here is a very simple procedure, and I'll explain it, and then I'll go through a little bit of an analysis of it. So the idea is that we're going to start off, we don't know what the sparse support set is, so we'll let that S naught be the set of all the 1 through n indices. We'll set our precision to be 1/2, so that's what that is there. So we'll use a precision of 1/2, and you'll see the reason for the choice for that is that this will allow us to obey our precision budget constraint of n that I mentioned just a moment ago. And what we'll do is at each step we'll go and we'll measure the indices in the current support set. So first of all, we'll measure everybody once with a variance instead of 1, 2, because we're using only half the precision at each step. And then we'll threshold at 0. And we'll repeat this process, only going back and remeasuring the indices that survive each thresholding at 0 step. And then the final output will just be our final set of indices that exceed 0. As I mentioned, if I let little s denote the number of sparse components, the reason for the choice of taking the precision to be 1/2 is if you just do a little simple calculation there, you can see that the expected total precision is going to be obeying our constraint of n. So that shows that this kind of procedure takes about a total precision of n again. And now we're going to look at the probability of error. And we can break that into 2 components, the number of the false positive and the false negative errors. And I'll come back and analyze those in a second, but just let me give you a quick picture of what's going on so it's clear. So here again is their signal. We're going to make some very noisy measurements of that signal. We're going to threshold at 0 because I'm going to assume throughout this talk that the non-zero components are positive, but that's just for the simplicity of presentation. It doesn't really matter in the rest of the theory. You threshold at 0, you go back. Now you're going to only remeasure at the locations that survive. And you're going to do this a few times. Threshold at 0, remeasure places that survive, threshold at 0, so on and so forth. And the hope is that most of the true signal components will survive this thresholding process, and almost none of the noise components will survive. So how are we going to do this? What's going on? Well, if you were just going to make one sort of measurement, you might say, well, and we have a 0 Gaussian and a Gaussian with a mean of mu, you might say, well, let's try to balance the 2 types of error. So we put a threshold right in the middle, and that area there would be our total error. But what we're doing instead is we're doing this thresholding at 0. So now we have 2 types of error on the right and left there. One is really large, like 1/2, and the other is tiny. And we're exploiting that asymmetry in the level of sparsity, and that's reflected in these, the way we treat the errors here. And that's what's going to allow us to get some gains over the non-sequential approach. So let me just show you how that goes. We have, first of all, the false positive errors, which I'm showing in magenta there. This is pretty simple. Basically, a false positive will happen if a noise component makes it through all these thresholding stages. So the union is over all noise components, and then we'll have a noise component leak through the process if on every single stage of the experimental design it exceeds the value of 0, which is what's shown there. And then just using a union bound and the fact that because the noise terms are zero mean, they're symmetric, the probability that a given one will survive a step at any stage is just a half. It's a toss of a fair coin. We have that bound of n minus s, the total number of zero components, divided by 2 to the k, where k is the number of experimental stages. The false negatives are also quite easy to analyze. We just have a union over all the real components, a union over the experimental stages, and we'll miss a true component if it ever falls below 0 on any stage. So that's what that's saying. And then we just use a simple Gaussian tail bound for that, which gives us something of this form. So it's a tail bound with a union bound. So you put all that together, you get an expression that I'm showing here. So those are the two errors summed together. We're going to be thinking about what's happening when we're in a high-dimensional situation. So in the high-dimensional limit, we want this to tend to 0. So to do this, we'll first of all deal with the first term. We're going to take the number of experimental stages to be something a little bigger than log n. What that's going to allow us to do is kill off that first type of false positive error. So that means if we have enough stages, the noise just can't leak through those multiple thresholding stages. And then for the second term, if you just look at what's up there in the exponent, all we really have to do if we want to drive that to 0 as n tends to infinity is have mu being greater than a square root of c log s log n for any c that's larger than 4. Okay? And that just kind of just pops out of looking what makes that exponent up there negative. And so this is a kind of summary of what we have then. If we're doing something non-sequential, the value of the non-zero components needs to exceed something like square root of 2 log n. That's what we just showed, and that's actually necessary. In the sequential thresholding procedure, mu will have a sufficient condition as long as mu is greater than the square root of 4 log s plus log n. And with a little more work, you can get it down to square root of 2 log s plus log n. And that's sufficient. So the point here is that if s is much smaller than n, then you're really comparing log n with log s. And that's the savings you get through these sequential methods. And this is joint work with Rui, Jarvis, and Matt, who are shown there. So let me kind of just show you what this means then in the fruit fly example. Just plugging in the numbers there, 13,000 for n, and s was about 100. What you're getting is roughly 3 dB gain in performance. So for the same experimental budget, you get double the sensitivity, or if you want the same sort of level of sensitivity and reliability, then you only need to do about half as many experiments. And so this is kind of just mathematical justification for what Paul was already doing and what was working well in his lab. So I'm just going to quickly flash up here. One question you could ask is this the best you could do? And the answer is essentially yes. You can look at this problem using kind of classical sequential analysis methods, things like the sequential probability ratio. And you can show that in the Gaussian case, for example, mu must exceed square root of 2 log s over epsilon, where epsilon is sort of the desired level of error that you're trying to achieve. And so the square root of 2 log s is a really fundamental limit that you can't improve on by any method. You can essentially achieve it using a sequential probability ratio test. The difficulty there is that to tune up the thresholds for that test, you'd need to know the sparsity level. So it's not really adaptive to sparsity level, and that makes it not very easy to use in practice. Sequential thresholding, we didn't need to know the sparsity level at all. It's fully adaptive to that, and it is essentially as good as the best you could do modulo this log n. And if you're worried about that, then that might be a problem. But I think that might be something that would be difficult to improve on. It might be the price you pay for adaptivity, but that's still an open question. OK, so let me kind of wrap up a little bit by going through an example in the spectrum sensing where the gains are can be pretty dramatic. And so the idea is that, again, we're going to have a very large communication spectrum, and we want to figure out where can we communicate. So in a kind of cognitive radio situation, for example, user would like to find an opening that it can opportunistically use to communicate through. And in order to do that, it has to actually sense the spectrum. It has to look and say, is there a primary user in any of these channels? And so what would happen is the guy would scan through this spectrum trying to find a hole. And you could do this one of two ways. You could just spend a certain amount of time listening, say a fixed amount of time, t seconds, at each channel, and sweep through that way. Or you could dwell as long as you need to at any given channel in order to try to quickly decide whether or not somebody's already there. And as soon as you see somebody's there, you move on, sort of a more adaptive approach. So in this kind of situation, you're going to measure samples of the channel, which are usually modeled as a complex Gaussian with a variance of theta. Theta is the key parameter here. It's sort of the energy level in the channel. You form a simple energy kind of statistic. You make, say, m sub I measurements of the ith channel. You square and sum those, and that gives you a measure of how much energy is in the ith channel. That's going to be gamma distributed with either a variance of theta naught, which is going to be the high energy state if there's a primary user there, or in the interesting case we're looking for, the low energy case is going to be 1. That's just going to be background level of noise. So this is what the pictures look like of those gamma distributions. Theta 1, that's the low energy situation. Those are the guys we're trying to find, the low energy channels where we have openings. And theta 0 is larger than 1, and that's where we have somebody occupying it. So what makes this problem especially challenging is that you have a kind of one-sided distribution. So the left tail of the null distribution just kind of piles up and actually has a kind of polynomial behavior there on the left-hand side. And it makes it very difficult to distinguish the two distributions. So that's what I'm showing here again. The nice thing is that the other tail that we need to worry about, which is the right tail of the alternative hypothesis in magenta there, is an exponential tail. So why is this good for us? If we do our sequential thresholding idea, we're going to try a threshold somewhere at the middle of the null distribution, or the median. So we have 1/2 of the mass over there on the left. There's a very tiny tail in the alternate distribution going down exponentially. And so we're sort of just flipped. It's like the mirror image of the picture we were looking at before in the Gaussian case. But we have this nice situation where we can just keep having the nulls away, and we only have to deal with this tiny little tail sticking out on the other side of that threshold there. So we're going to fix our sensing budget so that we have an average. Okay, I'm downtime. I'm going to wrap up. Average of m samples per channel. That's our sort of constraint. And the punchline here is that if you're non-sequential, the sensing requirements are going to grow polynomially with the number of channels you're looking at, whereas in the sequential case, you're back to this kind of log S behavior. And these are just some pictures showing that this gives you a kind of significant gain of 10 dB or maybe a factor of 3 to 5 times speed up in scanning if you do it. Okay. And it's easy to implement. That's the other great thing about it. You do it in the lab. That's Matt implementing it. The ideas are very simple. It's not just math. And I'll skip this. Jarvis is going to talk about that stuff. And I'll just leave you with the takeaway message that if you're non-sequential, then the SNR in your problem needs to grow like the log of the dimension, or even worse, as we saw in the cognitive radio problem. And in sequential designs, you only need to have the SNR growing like log of sparsity level. So there's a potential big savings. And I'll stop. Thanks.
We have time for just 1 or 2 questions when we get set up for the next speaker.
Yeah. Yeah. So there are two, in this sort of single threshold type problem, there's going to be 2 error tails that are problematic. If they're both heavy, then there's not much you can do. But if one is heavy and the other's still exponential, you can still get these nice gains out of this. In fact, that's sort of where the sequential methods really shine relative to non-sequential methods, when you have this heavy tail plus exponential tail. And that's exactly what's going on in the cognitive radio. Yes?
The K, the number of steps,
Uh-huh.
is locked up. And back to the slide,
Yeah,
the 13,000 feet, that roughly means about 13 steps.
right. Right.
And that's part of
So what they did is, so that in the experiments that Paul Ahlquist and his lab did, they just sort of did something that seemed sensible. They weren't guided by any real theory or anything. And there are other papers out there on sequential design and biological problems, but usually it's sort of just using some rough back-of-the-envelope kind of calculations. What we were interested in doing is actually quantifying this, and that's where this log n specification for the number of steps sort of seems natural and appropriate, but there may be. Right. Well, it's still log of whatever that big number is, so it's not that bad. I mean, yeah, I think there may be other issues that you want to consider when you do this. Maybe it's hard to do more than a small number of stages just because of setting things up or something.
We better move on. Let's thank the speaker again.